Okay, today I wanted to talk about RC circuits, by which we mean a resistance and, via a switch, a capacitance. Okay, so this is our setup. Here is the resistance R, here is the capacitance C, and let's say that there's a charge Q on one plate, minus Q on the other plate. And what we're going to do is we're going to close that switch and let that charge flow off the plate. So we'll have a current I, which will take me in that direction. So I is clearly equal to minus dq by dt. Okay, now, what about the potential across that resistor? Well, that's given by V equals IR, but it's also given by V equals Q over C, because it's also the resistance across the voltage across the capacitance. So I've got minus Q by dt multiplied by R is equal to Q over C, or to put it together in a slightly easier way, dq by dt is equal to minus Q over RC. Let's look at that. The rate of change of charge, the rate at which charge flows off, is directly proportional to Q over C, the voltage, and inversely proportional to R, which is slowing it down as it flows off. So anyway, so this is the equation we're looking at. dq by dt is minus Q over RC. If we can solve this differential equation, then we can figure out how Q behaves as a function of time. So let me remind you of a few things in calculus that hopefully you remember from your early calculus courses. Okay, so let's do a little bit of calculus over here. And for example, you know, I hope, that d by dx of e to the x is just equal to e to the x. And d by dx of e to the minus ax is equal to minus a e to the minus ax. Now that says that d by dx of e to the minus ax is minus a e to the minus ax. So if I put y equals e to the minus ax, then dy by dx is equal to minus a times y. So that's another differential equation. And if you stare at it, you'll see it's really the very same differential equation that we have right here. So this equation is really the same as dy by dx is minus ay, and that is, the solution of that is basically e to the minus ax. In this case, we've got a is equivalent to the 1 over rc, and x is equivalent to the time. And so the solution of this is simply that Q is equal to, let's put a Q0 in front, e to the minus t over rc. I put a Q0 in front because I'm assuming that it's Q equals Q0. I should have said that perhaps. Q equals Q0 at t equals 0. We start with some definite charge there. And then the solution, the complete solution, is that Q is equal to Q0 e to the minus t over rc. So we've solved this differential equation because we've noticed it's identical to the equation that e to the minus ax satisfies. And we just equate the corresponding terms, and there we are. That's the solution.